As you just heard, I'm Carl Gunnar Årsæter. Today representing SINTEF. Usually I'm at the university. So, we are talking now about co-simulation in the maritime domain. And it's been used as a industrial and scientific tool for many, many years. From detailed component models all the way to training simulators. So simulations has become an indispensable tool. And now we are getting more and more requests or a trend at better and more detailed models. And for instance, for virtual prototyping, systems testing, assurances, digital twin application, and so forth. This the things we see in all industries. So the maritime domain has some peculiarities in both the organizational and technical layout. And one thing that has been developed is the open simulation platform that has been presented in a session prior to this one. It has been developed to ease the introduction of particularly FMI and FMU technologies in the maritime domain. So Open Simulation Platform was the first test or first version, and of course we discovered a bit of things that could be better. So that led to the SECO project that also been presented briefly. So SECO, its the main objective is to contribute to a reliable, easier to use simulation of maritime systems. And this is the important part, addressing the most pressing technical issues, because we experience technical issues once we start to use it. And the partners in this project is Kongsberg, DNV, SINTEF, Equinor, and the Technical University of Norway. And these are major players in the marine simulation domain in Norway. So in this presentation, we are focusing on how to place our models in a common sea environment, or how to work with the sea. So this is important because vessel design is a high degree of unique solutions. So you have maybe a hull series, different engines, different hulls, always adaptations, and then this ends up with quite complex interconnected systems. And all of these, does it work, this one? No. So all of these systems you see here, they are usually from different engineering disciplines. So, and we have used simulation so much that, of course, simulation has been used in all of these various, call it hydrodynamics, power systems, DP, crane, everything. Use hydrodynamics, simulation. And we end up with these, call it domain-specific simulation tools that are great. They solve a lot of our engineering problems. And but then you have the pressure to integrate all this into co-simulation models, to do more introductory work, design work, verification work. So co-simulation has been, let's say, seen as a solution. So it's popular, or at least we hope it's popular. So if we just go to the sea environment, just to give it a short introduction of why is it different in the maritime domain. So we place all this in the sea environment, and we have all these disciplines that are used to working in separate, answering questions, and now we have to integrate. So the sea environment is a good example of, call it, the issues that rise. This is, stop pointing. So this is like a common model you find in engineering textbooks for hydrodynamics of how we describe the sea surface. And then we end up with using potential theory or linear wave theory, and we make some assumption on how we represent the sea surface. At the same time, so we represent it with some harmonic functions and so forth. We have tools that work very well in this domain. And also we have empirical relationships that use velocities and accelerations. These are the things that if we are to place all our models in a common C environment, then we have to make sure that we can support this, and that we have a way of communicating this, and for instance, synchronizing both velocities and also wave fields. So yeah, this one would describe only one wave, but typically we will have 50, 100 or something. And it's very efficient on its own, but in a co-simulation setting, it's a bit different. So our environment description must be compatible to, call it, the body of theory and the knowledge we use. So when we started this, we had call it a very abstract look at what we use when we have when we do marine simulations and try to couple it in different, call it, separate models from different domains or different suppliers. So basically, both equations use acceleration of gravity and some densities, so they have to be same. You would be surprised how much 1000 versus 1025 crop up in computer code. So for the density of water. Then for the empirical values, we would need fluid flow. We would need flow velocities, directions, accelerations if we want to use them. So we have to share this. If we are going to have something in a wave field that I showed you previously, we will have to somehow share not only the met-ocean description, but also something that ensures that we have the same wave field in the hull FMU, lifting equipment, and also environment if we want to visualize it. So this is how we worked with it to define this. So we started with the constants, then the fluid flow values, and then we realized that some models use global fluid flow values, some need input to local fluid flow values, so it has to be position dependent. Actually, fluid density can be position dependent for large scale applications such as seismic. And in the end, we ended up also that if you're going to combine thrusters, propellers in this together with the hull, there should be some interaction effects. This is by far the most difficult. So this is from the paper. We ended up with call it a level of specification, where we could call it classify our simulation models into how sharing of environment information was implemented, and how call it the feature that this enables. So basic constants, you need to have it from an assurance point of view. Global current and wind, call it in the origin of your reference system. Then spatial and time varying current and wind, you input positions and you get back other values. Synchronize the wave definition to have the wave energy represented identically in all FMUs, and then propulsion interaction. So we made this specification levels. So for this, we made a use case, or for marine lifting. Why we use marine lifting? It's because it's a quite complex operation, both simple and complex. It is one vessel with a crane on the ocean. So we implemented this to mirror this NTNU research vessel with the crane, and we had separate FMUs for the environment, the hull, make it seakeeping model, separate environment for the crane, a separate model for the crane, and also for the wave filter and control system. So we can have these three domains: hydrodynamics, deck equipment, and control working together. And I will not go into the details of these models. We have it in the paper. I'll call it the theory behind it and everything. But in this case, it's more how we implemented the the simulation and sharing of values. So, but marine lifting is quite an interesting case. So, we created these FMUs. We did it with what we call FMI CPP, a CPP-based framework to make FMUs, just because it's our preferred toolchain. And we ended up with what we call a big bus interface that we decided to share these values with the coupling or port system in FMI. And then in FMI 1 and 2, we only had support for 1 and 2 in this tool. So we are aware that FMI 3 would solve some of these challenges, but you get port layouts like this. That also was shown in the previous presentation. It is unworkable unless you have some extensions. So then we use this open simulation platform that has been developed for marine use, and this variable group feature that allows us to group all of the wave heights in one group, all of the wave frequencies, and so forth, and just connect waves like 3 and 4 ports. This is not the this is not the ultimate solution to this. This is a workable solution that that we implemented. There are what we call it, many ways to roam. It depends on the people who make this, what they prefer. But we think this specification level is that is a useful feature. So this we implemented this. We run it and call it a demonstrator. One thing when we do this, since we work with these tools in hydrodynamics and offshore lifting and so forth, we have the need for pre-processing. So especially for the seakeeping behavior of the hull and the motions, the forces, we have to pre-process it to have it workable in FMU. And that sort of limits some of the effects you can capture. So in this figure here, it is from the post-process visualization. You see the wave field in the environment, but you don't see the refracted and diffracted waves from the vessel. Those are in the vessel model. They're not in the complete or the system co-simulation. So we did 2 seas, one moderate, one quite severe. This vessel is quite small, so it will move a lot on these seas. We put a payload on the crane, put it in call it the wave zone, leave it hanging there for 10 minutes to simulate how our payload interacts with the water. And then also we simulated for some hours to lower the payload through the water column. That allowed us to look at how it would work with getting current and wind values as the payload descended both in position, so the current would vary over the water column, and also in time. So we had this post-processing that we did based on the separate FMU results, just to be sure that everything worked as intended, because that was one of the difficult things working with distributed things. Another work package of this SECO project is coordinate transformations, and we worked a lot with that in the same time. So we have one type of FMU in the control system that interacts with the environment. It interacts with by the motions of the vessel. Its job is to remove wave frequency motions and make something that's controllable for the system. In our case, we didn't connect this directly to the environment, but it's very common to have a feed forward, that you have a measurement in the environment and feed it through a force model into your wave filter to recover phase. So, but this is not, this is call it a simplification in our model. It's not anything to do with the specification in the environment. But it works quite well, and In the simulation, the DP controller works to keep the vessel in place in the environment, compensates for the forces experienced by the vessel. And at the same time, we have, this is from the crane FMU, we have wire tensions, we have computation of wave forces and buoyancy forces. So this is from the lowering operation. So then you have some minutes with the payload hanging in the air, affected by wind, and then it starts to enter the wave zone, and then you get some smallish. This is not. This is only pressure, the normal pressure forces. So they subside once you lower it through the waves, and you have this call it stable oscillations in the tension due to the vessel pivoting back and forth. And then you have the position traces of the payload and the ship and the crane tip. And this is when it's in severe weather. So we have this, and then we see some expected things. We see that the waves go deeper, oscillations are harder trajectories. So this works quite well. We also have the, when we go down, we can have a look at the forces and see how they correspond to what we expect in theory. So this is force levels plotted by position in the water column. So then we have you see the exponential decay of the wave force, and also an exponential decay in the drag force because the current is varying in the column, in the water column. And we have, for severe weather, we have, as expected, wave forces are decreasing, but they go further down. We have a lot more drag force because everything is moving back and forth quite severely. So this thing shows that we have, call it, successfully synchronized our environment between the vessel and the payload, and also in the visualization, and then we can connect it to the control system. And the way we do it in the paper, we transfer the wave field on the port system. It becomes a lot of ports, but it's doable to reconstruct it. And once you reconstruct it, if you use the same theory, same axis system, you get the identical results. So for us, it's important to consider the current toolchain in the marine industries. And this is not just FMI, but the current toolchains that engineers use. So the toolchain that deck machinery people use, the toolchain that hydrodynamicists use, and the control people. And I would say that this big bus support, approach is not sustainable without additional tool support or FMI tree. But we are lagging in this open simulation platform. We don't have this FMI tree, so we can't leverage it yet. It's quite trivial to extend this. It's just port connection. So we have an environment you can just connect, and add. And this specification levels, so how we made it, it doesn't require that there is a specific environment FMU. You could implement the same, call it feature or interface on the hull. So you could have a hull simulation in your setup that exposes this interface, and then you could have easier access to make more expose local effects in the global simulation. This is just one solution. There are other solutions that we have considered and tried. We have done shared libraries with deterministic implementation of or control the random numbers and everything to make it perform the same realization each time. This does not accommodate inter-FMU interactions. We're not quite there yet, but it could be a workable solution. But on the other hand, we find it a bit more difficult to control or check our environment specification and which values we use. So in this, it goes over the ports. It's visible to the tool. We can, for instance, we can check that our natural frequencies are covered in the frequency selection in the C environment. And also we can use this coupling between the different models to call it detect what level we are. So if you receive current information, then if you output position back, then you are at the level 1. If you only receive but don't output position, you're level 0. If you consume wave information, you're level 3. So this is detectable in the tool level. So we can actually check if the model performs as expected or as stated. Yeah, just a short, there isn't any particular scientific conclusions other than this works, but we introduce simplifications. There are effects that you need to take into account or be aware of. Interaction through the environment, like you can do in regular engineering tools, where you have everything in one place, it's much more difficult. And those things are, call it, left for further work. Yeah, thank you.